company which I just learned is called Bell Labs. At least that's what we think it is called. You know that there is a lot of changes now in Bell systems, so the names may not be exactly accurate. What, however, is accurate is that Dr. Atal joined Bell system more than 30 years ago, in the early 60s. That was in the days when you talk about speech synthesizer, you talk about a box which was taking half of the room and it was full of coils. And of course, obviously, it was a research topic. Recognizers maybe attempt to recognize 10 digits from a single speaker, and again, nobody would even consider seriously that that would be a practical product. Nowadays, whoever uses AT&T digital service may wonder what is inside. And I can tell you that what is inside is, I would call it piece of Bishnu's brain, because Bishnu is pretty much, I think, single-handedly the most responsible person for speech coding as we know it today. He introduced linear predictive coding in early 60s. He introduced the multipulse and stochastic linear predictive coding in 70s. And those are the algorithms which form the base pretty much of every practical speech coder in existence today. And it's all in a little handset. Recently he took even a larger challenge, and he is looking into ways how to communicate with the computer by voice. That includes not only coding of speech and speech synthesis, but mainly speech recognition. And this, I believe, will be his talk today. So please, Bishnu, Atal, and his talk.
Thank you, Hinek. I want to correct him. What you see in speech processing today was brought about by participation by a very large number of people. But what I'm glad to say is that when I joined Bell Labs, I was told if you work on speech coding, way out. I can go back to India right away.
Excuse me, could I have the speaker put on the microphone?
Microphone.
Yeah.
Yes, thank you.
Only practical use for a tie.
Perfect, thank you.
Yeah. And at that time, speech processing was not a fashionable topic. Life is much easier today. And some of you might have known, like John Pierce, who wrote an article at once upon a time that with their speech recognition, and it was not possible to work on a speech recognition area and have a job at Bell Labs. We were counting number of people who could be in that field on one finger. And today, we have about 50 people working in Bell Labs and 30 people working in AT&T Labs and hundreds of people working everywhere. And I say it's a major revolution in this field. We have created a piece of knowledge which is acting up. And some people ask, and that's the topic of the today, what's happening? I've been hearing this all these days. Anything has happened? And it's amazing when things happen, and things have happened like internet. All of us know internet is there. There's no problem. 10 years ago, to carry on a discussion of internet in an educated way among anyone would have been difficult. Most people will say, what are you talking about? I don't know what, this is not a useful thing, and all this and that. Every technology takes time. Whether it was telephone in 1876, it took about 30 years. PCs in 70s, even early 80s is a problem something. Today, PCs are there. Speech recognition is such a technology. It's coming up to age. It's the beginning of a big thing. And what I want to do today is kind of share with you 3 topics. First, something, where are we in this area today as a result of the work which has been done by Bell Labs and hundreds of other people around the world, which has brought the speech technology to a certain stage. Where are we today? What are the challenges we face today as we start on a new journey in the future, which is going to be very, very challenging indeed. The past successes are no guarantee that we will have anything left behind after 5 years. It may just disappear. And what are the new directions I think we should take, and what we are doing at Bell Labs. Now, why this interest in speech recognition? As you know, the machines are getting more and more powerful. It's obvious. a computer which once upon a time could handle, 1 MIP was a big thing. Today, 100 MIPS doesn't impress us, and we are away to 1,000 MIPS and even more. Memory chips, 1 kilobyte was big thing. Today, 16 megabit chip is around the horizon, and at one day we will have a billion bits on a chip. It is putting tremendous amount of sophistication and functionality in a machine, but the user who will use it goes on a different clock cycle. The human being change every million years. And we have a very large gap, and you can see the frustrations. As far as this technology was visible only in laboratories like here or Bell Labs, there was no problem, because each computer we have a lot of people surrounding. Every day I run around and take the help of very sophisticated people. This bug, this problem, that problem. Life doesn't go like that. Computers have to be used in a real environment. If it has to be used by millions of people, it has to go into a different mode. And that mode is that they are easy to use. Their functionality will be accessible to average person who doesn't have a degree in computer science or PhD in some other area. Voice recognition, people feel, is one of the vehicles by which we will make this possible. We have a keyboard, we have mouse, and that added. Without mouse, I tell you, the computers would not have gone to an average person. The typewriter demanded that you know exactly what to type. That means you have a huge slew of books ready to go with all the index to figure out, should I type remove for removing files or save this and that. Clicking the mouse and the graphical interfaces change the world. And however, they have a limitation. And limitation being, if you have a few things from which to click from, it's okay. But if I have a million things and it scans through, and to click will take me a day to find out what to click. Speech, people feel, and I think they're rightly so, is a mode where I don't have to know exactly what I have to click. By talking a little bit here and there, I can figure it out, and that's what I do every day. You talk to a friend and says, well, I don't know, I want to go to Europe on vacation, I don't know where I should go, tell me where I should go, and he tells something, you go, and back and forth, and after a while you have the whole program charted out. The speech has a mode where things don't have to be precise. You don't have to click, but to be useful, the people have to feel the voice mode is like a clicking mode. You say and something clicks, although you don't raise a mouse. And this is the challenge we are facing. And so there's a great future, and rightly so. People say, when can we have a voice interface on top of graphical interface? Things are happening. They are not there yet. Today, very few PCs, although they offer speech, no one uses it. Apple has a speech interface. IBM has it. Most of them are kind of lying into a little sleeping mode. The new applications are emerging. I will share with you what has happened. And there are two worlds today. One, I mentioned computers getting sophisticated, but even the telephone is getting complicated. This telephone which you see here was a thing to talk to friends on voice. Today it's used more and more as a device to connect to machines. The telephone lines, computers always connect through modems and all that, but even when I talk to call a number, what I find there is that some machine comes in and says, if you want this, press 1, if you want that, press 2. And there was a cartoon in a newspaper some time back that if Mr. Watson in 76, Alexander Graham Bell would have called Watson, he would have gone, if you want Mr. Watson, press 1, press 2, press 3, excitement would have finished by the time he gets. And ultimately he would have got music on top of it. And so even for telephone use, I think a speech mode can diminish some of the pain and suffering people are going through today, because all the companies want to save money. They save money by replacing human beings with these machines, and their purpose done, and the problem is dumped on the user. And speech and voice can play an important role there. Now, where are we in this area? Instead of giving you a lot of lectures, I thought I plot on a two-dimensional plot, the vertical scale is how we say things. One word at a time in isolation. Do I read speech, or should I speak fluently, or should I just talk like we talk at lunchtime? As you know, as you go up in the y-axis, things get more and more difficult. If I speak every word like I speak every word, life is easier, but I can't talk that way. We like to talk the way we talk at lunchtime, but maybe we can settle for fluent speech. To write everything first and read it is impossible. But that's the dimension of difficulty created by speaking style. The x-axis is the size of vocabulary. How many words? Few words, easy to do. Large number of words or unlimited words, very difficult to do. Here are some of the things which we have learned over the last 20 years of research we can do to some reasonable degree of what I call proficiency. And thus, these things are ready and in fact are already gone, are going to the real applications. They don't work perfectly. They don't work as well a human being most of the time will handle it. But they are above a certain critical level of minimum performance that they can be put to work. And further, lot of learning of these parts have to be done in a population of real users. And this is one lesson I learned. Speech research cannot be done in the lab completely. You can start it, but no amount of database checking, no amount of 10, 20 speakers can represent 250 million people, just in the United States, who can access to your application. And we cannot model them. Only way to learn is to put that there and try to find your way to succeed in that environment. So applications are not just to make money, applications are to learn how to face the variability which exists in speech. And that is the difficulty of speech recognition. It looks so easy. All of us can do it. There's no problem. What's the problem? Problem is there are so many ways you can say the same thing in so many different environments, on so many different media with so much distortion, and it's a wonder that anything is possible. But that's the beauty of speech. That is so flexible. No matter what happens, I can carry a conversation. Noise, no noise, distortion, no distortion, foreign accent, I come from India, don't know how people say, I say life goes on one day. This is the nice thing about speech. And if we insist that our recognizer only handle those people who are born in America in a certain region of the country, have learned the right way to American English, it's better not do it, because half the people who come here in our airports are coming from some foreign countries, pick the telephone and start saying things, and they don't know what's, and that system has to work. And that's the challenge of the speech recognition. And that's what we are learning. So let's take some example, word spotting. Word spotting is an ability to spot few words, in this case I feel 10 words, in running speech. Those words are special words. You want to recognize them because by recognizing them you can do something useful. For example, if you dial 0 today on any AT&T operated telephone, you don't get a human operator. This happened about 2 years ago, and now anywhere you don't get it. You get a machine which will tell you something, and you have to say things. And it's a simple conversation. Try it at your home and see what happens. It works. You can make a credit card call, you make a person-to-person call, you make a collect-to-collect call, a third-party call, all by talking to a machine, and carry a very simple-minded observation from a device which only knows how to recognize 5 words in different conditions. It works very well, 5 words, but under different conditions. It is handling today something like 500 million calls every month, with 98% throughput. That is 98% of the time AT&T doesn't get a human operator involved. But if any time you set operator, I want an operator, or I say, what is this going on? I want operator, and operator is there, so customer feels somebody is always there ready to serve you. So people don't feel frightened that, oh, this is a machine. But it's a very successful thing, and AT&T, of course, saves money. Saving money through a procedure which you may not like, namely not getting operators to attend to your calls. But that's the process of automation. And it gives more flexibility. If I have to insist that new services will need an operator, we cannot create services, they're very expensive. By having automatic means to serve the customers, we can enhance the possibility of functionalities we can offer on the telephone by almost unlimited amount. And that's the new future. So it has two sides. On one hand, it automates. Some operators will not be able to do operator's job, but it gives flexibility. And this is very successful. AT&T saves $250 million year after year after year. Of course, they will say, let's forget about it. That I save, I don't want to learn. In terms of, if I say as a speech researcher that I am saving AT&T $250 million, they say, even if I don't have you, I will save $250 million because operators are already gone. That is correct. But this is a fact. That's the bad part of life. That you did it, good. But now, create another $250 million of saving every year. And then it's good. Not easy. Thank you again. But again, 250 is like, you get some robot who is bothering you all the time. But in any case, it did catch the attention of a company like AT&T, and they got so excited. So they make speech as a main strategy to succeed in this complex market. So that every service of them will offer very new functionalities. If they don't have a speech, it will be so expensive they can't offer it. They will offer new services based on a speech which are economical and will add value to the customers, which we have to see whether we can do it. But that's the strategy of AT&T's success story in the future. Rest will be all buying, merging, fighting. Technically, that's the only one strategy. Word spotting is coming to phrase spotting. Phrase spotting is a little more difficult, but if you have to distinguish 10 phrases, no problem. It's much easier than 10 words. Because if I say a word like no, yes, oh, a, very difficult, I tell you, these short words. If I say I want to distinguish 10 phrases, if you want, please press 1, and so on, no problem. Because the likelihood discourse by which we distinguish becomes more and more central and narrow as the length of the utterance increases. Digit strings, very important part of this. If you cannot recognize digits, you have no credibility. You can do everything, but what do you mean? You can't recognize 10 digits, forget it. But they're very important for banking, for credit card, account information. Like if you have AT&T universal card, and if you look at the back, there's 800 number, call it. Immediately a machine will come and do everything about your checking inquiry automatically. And it has 95% success rate. That means we have reduced the number of operators by a factor of 20. Well, universal card is happy like, they want more of it. They said, what else can you do? So there are 16 digits. 16 digits to be right have to be very right. Otherwise, it doesn't work. So that can be done. That's not a future. That's today. Speaker verification is who is the person who is speaking. Sprint offered this service 2 years ago or 1 year ago, and these services are coming up. They will check. The computer will figure out whether you are the right person or not. Voice commands, very important, but very reliable. Command mode is help. If you say help, no matter who is, computer must say, what can I do for you? And not help confused with something else. Recognition of one single command word reliably under any distortion condition here and there is very important. And similarly, maybe other command words. I wanted to show you actually a little demo, but which I will not show because we get a feedback from the loudspeaker. Generally, nobody has to hear that. I can listen to the telephone. But loudspeaker goes in the room, and room goes to the microphone, and we've set up a singing path. It creates a problem here. Here, I can say, wake up. The name of this is a voice agent, Maxwell, the familiar character in TV. I can say, Maxwell, go to sleep. Well, Maxwell understands go to sleep much more than anything else. If I say, Maxwell, wake up, it has been trained to understand wake up very well. And Maxwell, goodbye, he knows. There are a few things it knows very well. And command words have a good advantage, but they must be reliably verified. Name dialing, very important, simply because although we dial digits all the time from home, sometimes we convert to a speed dialing. When you are traveling, it's a nuisance to remember the telephone number of everybody whom you want to call. While travel, this is a service which AT&T introduced year before last, I think, or last year. I don't know whether you can, you can see it. This is the view graph does create a problem here. Just let me take me out from this. Is it? No, not better. It says with AT&T voice line service, you can make AT&T calling card calls with the sound of your voice. If you have AT&T calling card, there is no charge for this. Call this 800 number 994 voice, no additional charge, and you are on the service. From that day onwards, you can produce voice labels of any kind, like in example, call home Tony, lawyer, or anything. And you can call anywhere you like. But additional things like you can set up conference, like you are talking to a person and you have to add on a person, you press **C, and immediately you can say add Linda. And Linda will come there. And so you can have conference calls and all this. This is just the beginning of all these things. A very simple-minded thing, but very highly effective and useful. Voice transactions are coming up. If you want to make a reservation for a car or a hotel or an airline with a properly prompted dialogue, which is infinitely better than 1, 2, 3 business on a touchstone, you can complete your reservations. And that's coming. It doesn't require any high, very big advances. Reasonable amount of knowledge we have gained is ready to produce those applications. So you see more and more of these applications developing as we go by. This line separates what I call the present from the future. This is what I say is ready to go, already have gone, and creating large number of applications with AT&T and many other companies. This part is within the labs only. It is not ready to go outside because we find moment we do something realistic, the performance just goes to pots. And the reason being, the area which is on the left side of the dashed line succeeded based on acoustic modeling. The area on the right side needs sufficient knowledge of a scientific kind, not just ad hoc, in the semantics and the language modeling. These are the great challenges of the future we must bring to our own understanding range if we have to succeed in this. Otherwise, they will remain applications about which we talk, but will never move out anywhere. Yeah?
If you do the acoustic modeling better, can you do the semantic modeling less well? Is there a trade-off?
There is a trade-off, except when, you see, 10 digits I can say, 10 words I can say here and there. Continuous speech, if you give me, for example, 1,000 words and say, please speak only those words, essentially I will not speak. If you give me a new piece, say, follow my grammar, not the grammar I have learned in my childhood, and give me 5 books to read and say, use the words this way, I will not speak. We use semantics and languages to manage fluent speech and narrow down the range of search from unrestricted size to a manageable size which acoustics can handle. How much acoustics can handle is subject of dispute, At present, our acoustic knowledge is as good to handle a selection in continuous speech of something like 20 words. My feeling it has to go to 200 words before acoustics is in good shape. But 200 words is not unlimited. Rest is governed by semantics and language. And I will comment on that. It's an area of a great challenge. That means we are back to 1969 or 70 now. We know nothing. We have to start creating a knowledge from that basis. And I will comment to why I am so, little negative on what is happening today. It's not that nothing will happen, but we have to go seriously into the scientific mode to learn about that topic. And it's not an application mode arena, although it's not like just trying out a few things. And it needs investment in science for the next several years to come to a level where this thing will start growing. Where acoustic side also needs investment in science, except that we are already there. A lot of things will come through a process of continuous improvement, and a couple of breakthroughs will put us in the right chart. With semantics and language, my feeling is we are way, way behind. Now, we have made a lot of progress in acoustic side and partly language modeling side by a process which we are very proud of. The process was, we defined we didn't say we had to handle all the speech. Under a lot of research laboratories, we collected database, a large database, maybe 100 hours of speech. And we say we want to recognize words in that database. We divide the database into 2 pieces. One is a training part, other is a testing part. The training part was used to develop models. The testing part was used to judge how good it is. Whenever we did that, beginning, our error rates in digits were about 6%, which is a very high because 10 digits means 60% sequence error rate. In alphabets, it was 40%. In continuous speech was 50%. But we went to work on a large scale, and within 5 years, always we brought down the error rate, and error rate went down always. And we were very happy as we thought that's the way to progress. And that's how we got two results. Dictation on business news, 60,000 words in the lab environment of about 7%. Airline information dialogue, error rate of 3% we got. And we were very happy, but the moment we went to conversation, we got a very high error rate. And error rates which were anywhere above 50%. And over the last 2 to 3 years, dozens of people working are not able to bring them under the control, and it's shaken our confidence that are we in a saturation mode, or are we moving ahead? And that has large implications, I tell you, whether research community survives or doesn't survive. Because once we convince that our knowledge is stopped, and only thing is by some chance we hit on this database business and got this process, but that other process I have no inkling. It could be a 100-year project or a 50-year or never ending. Why do we want so many research people wasting their time? They should do something else. Because at that level, there are hundreds of topics I can tackle which have 200 years lifespan. We must establish credibility that we have enough intellectual power to develop scientific understanding of issues beyond what we have done already. To put the confidence back into business, into sponsoring agencies, whether it's ARPA or NSA or whatever it is. One thing I mentioned, that the creating applications for me like a religion, we said we must do it, and we forced AT&T to put the services at a great risk in the outside world. They say, I don't make, AT&T is a big company, $80 billion. If you make $100 million, they say, what's the problem? It doesn't ring a bell. So I can't convince them about business. They said, what's the problem? And $100 million business takes many years anyhow. So if I give $10 million worth of business, this is wasting of time. So we have to convince them that no, not for your business. If you ever want to succeed, we have to put real product and services in the marketplace. And the great risk, and I say we'll help them to manage the risk, but we put it. Don't kind of feel frightened to take the service and withdraw if it doesn't work and get it better. So in 1990, we put a very simple system in Telefonica in Spain, which is simple thing, 1, 2, 3, 3 words in Spanish, reliably from any phone in Spain. That worked, and we deliver a 5 ESS switch with this small capability. Well, it worked. So for the first time I got a check, yes, things do work. I can do 1, 2, 3 in Spain. We did in England the same thing with British English. It went through. We put this 0 plus. I said, if you call it 0 plus any area code, you get that. That went into 92. And then we put a mobile phone and so on. I won't go through the whole. Voice prompting is another thing. By few command words, you can prompt and navigate your path through a complex directory. That's a service we offer, and that went. Voice line, which I showed you the view graph with pictures on, that went into service. It's voice dialing. Universal card account information I mentioned. More recently, we have done name dialing again, and voice navigation, and Watson, which I would like to show you, but same thing as Maxwell, but I can't show because this is all going in. So it's not that these things are making a lot of money for AT&T. They are making a lot of money. If I was a private company, I will be happy to have all this business right away, because this business is growing at 40% over the last 5 years. Starting from a small number, and my projection, I don't want to, I tell you, I will be so happy to have a small company of that size, but for a company like AT&T, it will ring a bell only when it exceeds like $10 billion. I'll wait. But if 40% growth will hit $10 billion one of these days. But that's the challenge. And I cannot blame AT&T, that's their framework. They said, well, we are 80, and now we will, of course, going to grow after all these things, and we can acquire companies if we want to grow. We are only part of their equation. But for us to succeed and get credibility as that we know something and we can develop knowledge, we have to constantly push the companies, wherever they are, for putting this in the real world where it is tested by not 1, 2, 3, by millions of people now and then. So we develop confidence that I am learning something at least right. Otherwise, I have no idea. And that's one criticism I have for the ARPA program, because they do a database which has nothing to do with any reality, and I don't know whether we have learned anything or not. They might have learned actually, and we're sitting on knowledge, doing nothing. That's a bad thing. If we have not learned, that's equally bad, because we have wasted a lot of resources. Either way, it doesn't. So nobody has courage to say whatever we have learned, let's put an application to the real world and either make money or lose money, and we'll find out. And that's how we will resolve the value of that. That's as much about the present, more than I wanted to say. Let's move in the future. The present is, I'm very proud of what we have done. But on the scale of 0 to 1, that's 0.1. It's a long journey. And it will come only if we have confidence and go on moving with the full conviction that we know how to do research and how to create knowledge, and we will succeed. And I'm convinced we will do that. But it requires that sustained work. What are the challenges we face? First, robust performance. It means reliable performance. Ability of the recognizer to work well for different speakers and in the presence of noise, reverberation, and spectral distortion that are generally present on real communication channels. We are weak there. Automatic learning of new word and sound, not asking for new database collection. It should be a constant exercise. We don't need these databases all the time. It adds too much cost and doesn't give any confidence, because we learn only the databases, and it doesn't tell me whether I am generalizing or I am interpolating in a random way. What databases do is, you have a large space, you get samples from databases, you interpolate by interpolating functions. Sometimes they interpolate, sometimes they give you a false feeling that you are doing right, but this is garbage there. And when you try in the real thing, nothing works. And then we don't know what happens. So somehow we have to come to grips how to learn. If I have learned 100 words and I want to add 101 word must be learned in a proper way, and we need some scientific basis to learn new things automatically. Grammar for spoken language. You know, written, and it's my personal feeling, and spoken languages have something in common, but a lot of differences. The reason being, if I have to write something which I will speak in 1 minute, it takes me at least half an hour. I write first draft, correct it, change it, do back, forth, back, forth. Why is that? Same person, I can speak for 1 minute, never feel ashamed of speaking wrong things. But I will not write that. Because the grammar for written form is highly structured to take account of a lot of other things. The spoken form is highly flexible. It is useful only because I can speak without correcting 5 times. If I go back and forth, you won't listen to me. Now, what is that grammar? There is a grammar there which allows me to have flexibility to introduce mistakes and learn from scratch as a child and get into the real world. We have to learn that grammar, the grammar for spoken language. Flexibility, same kind of comments. We cannot put restrictions on user. We can put some, but not too many. People won't use it, the markets won't develop. Another way of saying is, these are the words. What is the challenge for the future? If I take the present kind of progress we have made in the area of fluent speech, like dictation, transcription, and dialogues. If you look at the left-hand side from 90 to 1994, error rates have gone down to very reasonable values, and they will continue going down. But the moment you put some more realistic thing like broadcast news, television news, telephone conversation, error rates are here. So the challenge for us is go from here, somewhere 50 to 2% by year 2000. Question is, can we do it? And now people say, what do you mean by all this? I get into controversy. People say, well, I don't know what you're talking about. What database? Who collects it? What condition? So I prepare a videotape for that. I said, don't discuss with the database. That's your problem. Database is a researcher's problem. How do we research is not the problem of its task. Task is, I give you a short example of a little conversation which a user is carrying out with a machine. And if I can hear the videotape, that thing will be... Can I have the videotape?
Connect me to my network agent, please.
How may I assist you?
I need an analysis
No
for
sound.
investment in Australian opal. Access the AT&T knowledge
need-
source for reports
we
on
need the
Australian opal
sound.
for the last 3 years, and convert the financial data to my standard
Is there
presentation
audio here,
format.
button here or
Oh,
something?
and I also need a rundown on any recent partnership activity.
Please clarify recent.
Okay, can you back up,
Last
please?
12 months, and provide
You have to back up a little bit. That's it. I think we can start here.
sure that we cover all the details.
Okay, sure, it's your call.
Great. I knew you'd understand.
Ignore
Talk
this.
to you at 4.
Okay, bye now.
Connect me to my network agent, please.
How may I assist you?
I need an analysis for investment in Australian opal. Access the AT&T knowledge source for reports on Australian opal for the last 3 years, and convert the financial data to my standard presentation format. Oh, and I also need a rundown on any recent partnership activity.
Please clarify recent.
Last 12 months, and provide me with any video or text files on interviews with company officers for the same period. Store this in Preston Warner's client file for my review at 2 p.m. That's all.
You may also want to review reports on recent Australian legislation and litigation affecting gem investments.
That's a good idea. Thanks. Add that. And hold all my calls, please.
All calls will be held.
Please stop the VCR. Now, it has some semantic component, I agree. But we better be close to this if we want to keep progress. If you take the transcription job, any one of us can transcribe this with 100% accuracy. It's clear voice, it doesn't have noise, anything. But it has a way of speaking which we don't know how to handle. And that's one dimension is outside us. My feeling is it should be possible to do it. If we do it, then we get another 5-10 years to handle the noise and all this other problem. Then we at least on a steady program of success.
Were you talking about parsing, the and us, and what were you talking about the thing with?
I don't know how to do it. I just say what I would like to see happen. I hope we all as researchers will play our role in making this problem successful. Now, we have a lot of other things going for us. If we can provide the technical solutions, question is, can we implement it? Today, it takes a long time to do speech recognition research because everything is very slow. The training procedures take weeks and weeks on large databases the way we do it. We have to go to some other incremental style. But also, the search we do in a way which I don't know whether our knowledge is limited or our searching procedures are faulty. Because what we do is, the way we do it, we have these word lattices, which have a lot of branching. And if we take all branches into account, this whole thing grows. So we do what is called beam search. And beam is a good thing if you're in the right direction. If a beam search and where we want to go here, will never take me there. And we do partly this, we get lost completely. Now, if we have a large memory in the computer, we can store more things, and maybe your islands might be like, if we store real things more and more, we will never perhaps fall away because we know these are secure places. The memory sizes of the order of, I said, billion bytes will be available somewhere in the next century. So if we have a solution, they will go. Processing power of the order of 1,000 megahertz will be there as we go in the future. And this view graph kind of I took it from a magazine. This is a projection of the National Semiconductor Industry Association, which may be partly wrong, but they're not way off. It says 64 billion bits on a single chip by year 2010, and something like 1,300 megahertz on a single chip on a processor's side. These are very good results because we can use 10% for speech recognition, leaving 90% to do tremendous functionality, and everything will work. But we need solutions. Now, to meet these challenges, what can we do? There are hundreds of ideas, and those ideas should be pursued. I will just discuss my personal biases, the way I implement these things at Bell Labs. A Bell Lab, our research program, has 3 components. a significant part of our program is creating new applications using the existing knowledge and learning by continuously improving the performance. We should not deny the importance because that's our bridge to the future. If we don't do that, that means we talk, because we succeed in doing based on the past knowledge and establish credibility. Second part is taking brand new directions, which, according to my judgment, will lead to tremendous opportunities for AT&T and Lucent Technologies, and exercise them. There is a risk. Nothing may work, but we'll do it. And third thing is enjoy life a little bit. Play and have fun. Because a lot of good things happen that way. You are not doing something very great, but it so happens that they happen. And we don't want to miss that. So we have to be a part of that. What's the balance? As a, both at Bell Lab outside, we all should have these three components. Otherwise, we will not succeed. Unless we have a little bit of easygoing things, play fun, we are working all the time to do right thing, we will miss some big things. Now, our goal is voice communication with machines to provide universal access to information. That's the future. We are going from voice dialing, digit dialing, and all this to a continuous dialogue with machine, and where a lot of new things are happening. We want a speech processing capability to learn spoken languages the natural way, not the database way. A natural way is automatic learning of languages with minimal manual help. Some manual help is okay, but it should be all automatic, the way child learns. New acoustic units. I think it's wrong. What we do today is we collect a database, make a transcription in written form, which, as you know, has sources of error. And then we take a dictionary and convert it to a phonetic form, which has hundreds of errors everywhere, because we don't know how 100 million people will pronounce the same word different ways. We have no database. Well, we said, guess it. Anyhow, take a dictionary and put it. And then we train our recognizer to map and model our acoustics such that transcription looks closest to the phonetic form I came out with this cumbersome procedure. It has two sources of error. First, a human person listens, he gets tired, and he does something, he transcribes, and then we convert the text form to a phonetic form, which is prone to error, and then we use a training procedure to map acoustics to that, which produces wrong models. Then when a new thing comes, I say it doesn't work, then I get lost. No. I don't know what units I should use at the acoustic level, at the phonetic level, at the longer phrase level. We need units, because units is the mechanics by which I take continuous things and handle them. We need to have open mind and develop procedures to seek such units. And lastly, the reverse process of ASR, which is convert a semantic representation to acoustic form. Partly, all these are dealing with acoustic to semantics, ultimately, speech understanding. But suppose a computer understood, it has to respond back. How does it do it? Will it going to speak 5 different messages all the time, or it will be responding intelligently to the problems it faces? And we need that. The problem with this program is, where do we start? It's easy to say, and we get lost. Simply because speech is not spoken, although words, we hear words, but in the acoustic level, there are no words to worry about. This looks like a continuous waveform, continuous parameters. So this is the word for. Well, you may see here, but where is all these sounds for or? And to divide them up is unnatural. Well, there is an interpretation. There is somewhere a transcription at the far end which says this is a sequence of 4 sounds. Here, may we all learn a yellow? Well, I don't see all that. There may be a procedure which can interpret, but to say that we can artificially divide this in the very beginning at the acoustic level, all this is very wrong. And that's why our success in continuous speech has come about as putting a language model after this. And we need at least a trigram or a bigram grammar to get low error rates, which means we are using about half a second speech in chunks to make a decision. We cannot say within a half a second where is everything. It's all guesswork. Question is, how do we tackle this problem of finding what are the discrete units behind it, which is creating a manifestation of continuous speech? Before I could even look at this problem, it was just too difficult, and I don't know where to start. I said, let's take a much simpler problem, infinitely simpler problem. Take English text, which has a lot of spaces. In text form, we put spaces always. Not in Japanese, actually. There's a problem there. But let's take English. We put spaces, and every word is visible here. So I said, what I will do is remove all the spaces, number one. And then for computer, or for my intuition not to work quickly there, is to convert every letter to a new letter in a one-to-one fashion. So the text will look like this. This is as easy or as difficult as this. Question is, can I find all the words here? By a procedure which doesn't use my a priori knowledge of English dictionary, if I, of course, want to cheat, I will go to dictionary and say I know the words, and I remap them and say you find them out. That's not the idea. Idea is, given the text of a large amount, how can I find these words?
And you've taken the spaces out,
Yeah.
just annihilated them, not substituted.
Yeah, this is absolutely. This is just like, look, it's an endless string of characters. And if I can't solve this problem, it's a toy problem. It's very easy. But if I can't solve this, I will never solve the speech problem. I needed something to regain some confidence in that I should ever do anything in this area. So it took a very simple problem. So how do we do that? Now, I'm sure this problem has been solved 10 different ways. So, but I wanted to solve my way to learn the process, that can I think through without cheating? Because I could take a dictionary to help me out right away. So I'm assuming there's English language, I know nothing about the language, I know nothing about anything. Someone gives me just a string and says, go. I use a procedure which is like this. And this, let me say, this is not my own. Frederic Bambeau from ENST, French Telecom from France, came 2 years ago to work for a summer. And we discussed with this and said, let's try it out. The procedure is very simple. We assume we assume a continuous message is formed of concatenation of independent variable length sequences. The maximum length, I put it n. It's finite, otherwise my computer program will grow very big and memory will not. And then we tried different kind of n, 5, 7, 10 kind of things. Now let W1 to Wn be a string of n words, and let L be a possible segmentation of W into Q sequences. Ignore all this symbolic, but idea is we have now a sequence of words of some kind, which I don't know, and there may be a segmentation of this kind, S1 to SQ. We can compute the likelihood of segmentation if I know the probability of each word occurring in the language. So I have to make a model. If done that, I can compute the total probability, which I just state is very simple. It must be a product because I'm assuming they're independent sequences. The procedure is an initial estimation, just like any other HMM and all this. You start with some reasonable initial condition. You get a maximum likelihood segmentation into variable length sequences because you know the probabilities. You can do that. Once you have that, you can re-estimate the probabilities. Once you have that, you can re-estimate this, the words and continue doing it unless it converges. So it's derived, it's kind of derived directly from the kind of things we do in speech, but it's not a completely wrong procedure. It's something reasonable. It's not the best procedure, however. And for this, we needed some book in the computer. We have a big full text of a Bible, some chapters. So it doesn't matter what thing is. It looks like that. It doesn't matter what word. And I did the same thing as I said, converted them. And these are the first 50 words. And if you look, what we'll find later on as you go into the list, the whole thing has some maybe 900 words or something. And as you go, I can't put everything here, you get then a lot of fragments. Natural segmentation because I didn't have enough occurrences of the word. If one word occurs one time, there are any number of ways I can do that. And then it could compound words which occur in pairs. They became one word time to time. There's no way to reject that. So it kind of showed to me that there may be, what I'm using, what's the basis of that? I'm saying is if some pattern occurs consistently many times, you have to recognize it and put in the code book, because that becomes the basis of further classification. And you should organize those things into some order, so something which occurs once in lifetime is the suspicious thing, but occurs many times is a reliable thing, because I have a lot of models there.
So why didn't you choose letters then? Why did you choose words as your gram?
This comes with likelihood because I said the maximum length is, say, in this case, psi 5, I think. So likelihoods are not meant. You see, what happens if you use letters, you will get a smaller code book, but it will take likelihood is not as low as if you use a sequence like which or walk. Letters are part of the word list here, but only those letters like A and which occurs many, many times, because it will not make W as a letter, because W is a part of a which as a higher likelihood than W as an isolated word. We tried one more step in text before I went to acoustics. How am I running on time? Late? 10, okay. Maybe 5, maybe enough. I took the ATIS database. I said, this is letters. There's different tasks there. I have words and words there. There I don't know what is the phrase unit kind of words. What is the higher unit beyond words? Now there I have I don't know. But I said, let me use the same principle and whether this makes sense or not. So here are the sentences of ATIS database. Which airline departs from some city? There are so many city names. Find the cheapest one-way fare from somewhere, and so on and so on. We assume that phrases consist of no more than 5 words. This is an arbitrary thing, but doesn't matter. You can make 7 and all this makes no difference. The phrases came like this. Which airline occurred many, many times. So it gets 1 entry. So when you recognize, you can say which airline is occurring many, many times. From departs from city. Find the cheapest one-way fare became 1 phrase, and so on, so on. What is the earliest flight? What time does flight number arrive in city? Now, question, are they meaningful units? My knowledge stops there. Maybe or may not be. But it's interesting that these phrases occur many times, and I feel is and recognize that they better have some special status. I did compute some kind of perplexity style generalization thing, just a mechanical check whether it makes sense or not. I can do n-gram model, which we do all the time. 1, 2, 3, 4. If you do conventional 1, 2, 3, 4, 7 n-gram model, you will again get a code book of n-grams. For 7, and suppose you have 1, perplexity will be 81 for ATIS database, which is a high because a single unigram doesn't capture the word pair relationships and so on. And the test set is 92, reasonable result. We go to 2, we get 11 and 17. You say that's not bad. We go to 3, 6. Perplexity goes always down in training set, but in test set even 27, and we stop there generally. But we ignore it that something bad has happened. I have done something on the training set which says perplexity is 6. When I go to training set, doesn't apply. That means I have a lot of useless n-grams which don't have any existence except they occur in a mechanical way by my procedure of segmenting them into trigrams. When I went to multigrams, 2, in fact, 25, 32, 3, 16, 21, even 7 is 10 and 15. It's generalizing all the time. Perplexity may be higher than the training set, but the test set perplexity is controlled now. And number of sequences in the table of 7 multigram is 4,000 or 5,000. For n, 7 was 27,000. That means there are 22,000 unnatural segmentations, which has nothing to do with reality, create a lot of perplexity reduction, but don't generalize. So that showed me that there is a possibility to proceed on the speech side. But the speech side has more problems. Here, the letters and the words are what called representation, which have no errors. Each word, whatever occurs the same way. Each letter occurs the same way in test and training set. In acoustic form, each time I speak, I produce something different. So this is called noiseless coding. That's noisy coding, right? That's one problem. Second, the speaking rate here, I have no control. I speak slow, fast, and everything will look same sequence is spoken in different environment with different noisy conditions, and different speaking rate will look different. I will create so many sequences from nowhere. I have to have a procedure which will let me handle first noise. Noise I can handle by creating a criterion of some kind, which we are good at. We can do that. Some similar noise ratio. I use the entropy criterion or something. But we need a procedure which will not create a lot of variable length things out of different speaking rate. And I use a procedure which I had worked many years ago, which is taking a time sequence and making the thing discrete. That is, if I measure speech parameters every 10 milliseconds, I get too many of them. But they are not every 10 milliseconds. They are really much more discrete than we ever believe it. And that's something which is very old. It's based on a model that in the real process, driving speech is discrete. What comes out of this continuously is because there is a smearing and the context-depending effects created in the generation process. So it creates a lot of smearing, you get a continuous thing. Given yt, how can I find h and x was the problem which I solved. We apply the same procedure to this, and what it does is the following. So if I measure the acoustic parameters here, in this case they happen to be some formants, say 4, just for illustration purposes. This word 4 has so many of them. But we get these only 1, 2, 3, 4, 5 vectors here. So they became the input of now the next stage of work. So we took the whole, this we did for the ATIS database, which is about 20 hours of speech. We went through that, we got all these vectors. So they produce something like, I know about, on the average, depending upon all the conditions, like 20 vectors per second, roughly. There is an error always a little bit here and there because these are not perfect procedures. And then we define an entropy-based criterion similar to the maximum likelihood, but more using the error in matching things. And that work was done only last year in the fall. And we are getting very promising results. So we got now a lot of code books because so much data, and the code books is not only letters, but it is on this acoustic data. And then how do I know when anything good is happening? I cannot just watch letters and all this, so we're listening. And we are listening, what it's doing is taking units, some are monosyllables like pet, kid, and it segmented this thing, called them 4, maybe a unit, because 4 is used so many places. What it's doing is finding same thing occurring many times. If a part of a speech occurs many times, it gets an entry. Whatever occurs infrequently doesn't get recognized. So if I break up things in the wrong place, it creates a lot of noise, and that doesn't get into likelihood. So entropy calculation doesn't prefer that. So this is only a kind of a starting of this thing, but I am very positive now that we will be able to create units of different types, subword type labels, and then labels which are more like morphemes, more than like phrases, and further along, based purely on the data we have without any a priori assumption of what creates that data.
So this is still noiseless,
No, noisy. This speech is noisy. There is I didn't write the equation here. There is a criterion we developed, which is calculating the entropy of the representation plus the error together, and which takes into account the whole thing. So it's not noiseless, it's a noisy coding because it takes the error of matching into account in determining the whole procedure.
This seems like you get a lot of people calling from the airport, it's going to detect an airplane in the background as a phone app or whatever.
Quite possible. Right now I'm using ATIS data, which is clean. You're right. I have not even gone to that stage. The noise does additional things. And however, I am kind of somehow assuming in back some part of my brain that some of the things like Hinak is working and other people are working will start working. And then we will write. There will be procedures which will handle those situations, I think, better than I handle today. But that problem is simpler in my domain than this open-ended problem of what do I do, where do I start. It's completely open-ended because I don't know where to start. Once the framework gets a little bit contained, I think I can open up a lot of issues. But I did it, in fact, last year, to just get some feeling whether the procedure for automatic learning without assumptions about the structure of the data can work at all, or it's like a lost cause. Immediately I have to then start putting assumptions in, then I become dependent on that. Yeah.
Neural networks, I'm sure you know, behave very much like what you were saying that was needed. They can respond to noise. They learn by themselves.
I missed the first part of your question.
Neural networks?
Oh, neural networks, yeah.
I was just wondering if there are applications of neural networks to speech. And
I'm not the right person to comment on that. I'm sure there will be a proper procedure, but I want to keep my, this is a very difficult problem. I don't want to say that I know what will work, and I don't want to limit myself to the existing procedures. I'm saying I have a problem. How can I go toward the solution and start moving along closer and closer to my goal of, I say, learning a language by minimal amount of manual help without assuming anything about the units of how we decode, classify things. And maybe neural network certainly will be useful as a mapping device somewhere because they are nonlinear mappings. But I don't know directly how will this resolve my problem. My problem is how to get continuous thing into discrete form, not knowing what I'm talking about. Like, the thing is, problem is like, if I take a signal, I can always convert to sine waves, right? If someone says right or wrong, there's nothing right or wrong. It's a complete set. I can take infinite number of orthogonal sets which are equally right? And that shakes me. What am I talking about? I want to see whether in speech, nature has built in some kind of discrete structure which can be learned by themselves from the language by using the language itself. Is this assumption or it's some thing? I cannot assume for a time signal that nature built everything to be sum of sine waves, right? That will be wrong. Immediately you say that's wrong. But here I'm saying is maybe in this signal, the way we create languages is we bias it in terms of non-uniform frequency of occurrence of the proper decoding units. And then a person can learn those decoding units by just listening to language enough for a few years, and then she learns it.
Trained to a variant of maximum likelihood, how was it not? What was it different? How was it not?
No, maximum likelihood itself cannot work here because there is a model based on the code book and there is an error in matching. You have to include both, and then you can call maximum likelihood if you like. I have no problem, because whether I call entropy or likelihood, that's a small difference. We use an entropy-based approach, but there are a number of variants of this. But main thing is you have to represent the modeling error both in terms of the error as well as in terms of code book. Otherwise, I will take a very simple code book, put all my problems in the error, and say that everything is very good. So if you do a bad modeling, error entropy went up, and it keeps things under bounds. Yeah.
If I look at something I would regard as a simpler problem, 30 years ago or more, people were talking about computers playing chess. Just have a recent... they thought computers would be smart and understand the overall structure of chess. And yet if you look at recently, the computers basically evaluate billions of positions. They're brute force playing chess. This seems to be much harder than something like chess. And you're kind of trying to find some little magic things which will simplify it enormously. But yet, they've taken simpler problems and they haven't found the magic things. It seems like you could spend another 30 years looking for how to simplify this stuff and not find it. And then the only way you could do this is just by brute force, and 30 years from now we'll have the hardware to do it. But I mean, is it possible you guys will not find these little simplifying things?
Quite possible, because this is the nature of risk. I said three things we do. One thing is I try to use my old knowledge, maximum way, to create products and services, and continuous learning, with a lot of incremental work, little polishing, layer tune-up, and that keeps train moving. And we spend, today maybe, too much maybe, 60% of our resources there. But I want to spend at least 30%, that's the imbalance we have slightly, 30% on people saying, let's try that. 90% they won't succeed, agreed. But if 10% they succeed, it will build our future. I don't need too many new ideas. In 30 years, if I can get 5 ideas, I am successful. So I don't care if people create a lot of useless ideas, I can absorb all that. But if you don't, 0 is a bad number. We will get demolished. So my fear of not getting even one solution is driving me. You are right, chess is brute force. Here, what I don't know, if I could talk to God and ask him how made languages, then I could get a belief. It's only by trial and error. You create a model, check it, and then there's no basis for that. My own feeling is brute force is not the right name. We will use large memories to store, no question. Speech recognition is partly a search problem. No matter how much modeling I do, I will have a code book of such large size. Somebody has to find out what are the sequences. I don't deny that. But brute force cannot be used not to, this is too big a problem. If you take speech, endless amount of explosion of information will occur. No computer can store all the speech with all the human beings create for the rest of their lives. So we need some insight of how to make a manageable decoding strategy, which is derived from the way nature has produced it. to be used for communication. And that's where we are struggling. We have no idea what nature did, and we are saying, maybe nature did this, and we have to guess. And that's where the competition will come. Once we have the right strategy, we have some glimpse of what nature could have done, I am sure a lot of people will solve the other part of the problem.
On that theme, do you ever explore non-speech listening, such as music or other...
It's a very good question. The person who worked on this, I didn't work directly on this, I don't have time. He was from Cornell, and his professor, Professor Parks, asked him to think about the whale sound problem. And when he came to work with us, he said, do you know anything? How do I will classify all the whale things? Whale produce a lot of records, but I have no idea what the sound, what not. And I said, well, that's something, why not I convert to speech here? And music in the same category, you're right. So we have to, the same ballpark. Now, what I don't know whether the language of speech and language of whale and language of music have something in common. I cannot say that. But I am saying somehow, from a communication point of view, if I want to communicate to you reliably something, either I give you all the codes in advance, which then you can use to partition the continuous messages, or give you a framework in which you can figure out how to decode. Only thing somebody has tell you, I am using a strategy of those things which I want reliably occurring are occurring lot of times. You can learn. Those things which don't matter may not occur many times, and you can forget about it. Some such rough strategy I am using. Is this a sound principle? I don't know. But I would like to learn what are the principles by which, if you have to design a communication system for a speech communication, how will you go about doing it in presence of the variability we experience?
If you had to give federal funding sources advice on where they should invest, what would be the high payoff problems that you think ought to be invested in from the scientific and technological point of view to bring your vision to fruition? What percentage of things, where would you put them? What categories? I put 40% of my investment in acoustics, or 20% or 10%, and the rest in... What would be your portfolio?
Yeah, it's I don't know, but I'll tell you, share. It's the way the federal agency, the people whom we deal with, because what is a federal agency? How high level I go? And that's one problem I find, that the pressures build up along a dimension which are inconsistent with the desire to succeed. And you can't do anything about it, because you don't have access to the real guy sitting there. If you talk to a real guy, you will get a good agreement. Fortunately, in AT&T, we were able to penetrate the barrier, because if we get middle managers, they will give me a lecture of useless kind and it doesn't work. At the highest level, I can ask them, do you want to succeed or not? Yes. Okay, let's sit down. And they may not buy it, but think of it, federal government or AT&T. AT&T spends a lot of money on R&D, right? They will take a risk if I don't tie up billions of dollars in R&D. If I say I have a program of $10 million per year, right? I think it's easy to convince the highest management, not the middle management, that it's worth risking because it's not all absurd. They're giving the same talk. They said, yeah, go ahead, do it. I identify. If I give the same talk to government, if I give the same talk to AT&T middle manager somewhere in business unit, whose job depends upon a little thing, he will get a faint. He'll forget about all this. He will never approve this. But I don't need approval. I get the funding from corporation, right? So I only go to, there are only a few levels between the vice president for research and the chief of the company, so we can... Now, same thing, if you could go to your funding agency boss somewhere, who only had to struggle with Congress, that's about it. You can succeed by doing things right. That is, then you can say, by your assessment, you can do the assessment right away. Acoustics is a problem, but it's not a problem which will kill speech research right away. It will kill it ultimately. Okay. But if you don't get a handle of semantics and natural languages in a manageable way, it will kill everything anyhow. So you have to see, pardon? Okay. You have to think of long term in a balanced way. So it depends on how much money. Like in Bell Labs, you might say we have acoustic modeling, maybe 20% people working, right? Not bad, they're enough. But 20% doesn't solve my problem. The people have to take it seriously. They don't take it. So they do incremental work, and that kills me. It's not funding part bothers me. It is, they do it because they go to meetings. They say that's the prominent idea. And no amount of lecturing, people don't want to take risk. I say take risk. But they say, well, I don't know, they want to succeed. They want to succeed right away. And there's nothing I can do to make anybody succeed right away. So everybody has to take risk. Risk with the career, risk with his job, and government will also do it. AT&T does this, and things will work. But it is manageable. But it's not 2030. It's everybody who does in acoustics has to think this is his mission. That's it. And I think solutions will come. Same thing about semantics, language modeling, and so on and so on. We need new approaches. That's all I can say. And I think people will enjoy doing that. They don't do it. They are fearful that somewhere somebody will cut their funding off. I think I to stop.
How much innovation do you expect to come from the user community as we see things like wildfire and other speech-enabled applications starting to show up? Do you think that's going to help the roadblocks?
Not on the fundamental knowledge, but they do clear roadblocks on the application side. Like I couldn't show you the Maxwell here, but these are they make you aware of the application side. That's as equally innovative approach. How to convert this knowledge into useful applications, which our customers or whoever uses will say, oh, this is real wildfire, right? That's also, but that's, I didn't touch upon that, but you need that too.
We take one more question. This is the very last one to hear the wisdom.
No wisdom.
Haven't heard many students.
I have a question. If you go back to your videotape, how many years away are you from that person sitting down in a laboratory and doing what she did? And how many years away are you from the average office worker being able to do something like that?
Okay, this nice thing about research thing is like, I can do whatever I like. This is one thing I do because nobody's going to kill me about this. 5 to 10 years, this will happen. But research, you can never think it will most certainly happen, otherwise it won't be research, right? Because this is probability a little bit coming in there. But with a high sense of confidence, I say, within 5 to 10 years, you will see this happening in your office environment.
Okay, Bishnu, thank you very much.